Perfect.
All right.
Yes, we can see it in full mode. Yes, great. Thank you.
So perfect. Thank you very much. Thanks for the intro, Gabriel, and thanks to all participants for looking into it today. So thank you. I feel really honored to be invited for this, and thanks for SPE for hosting it and for organizing it. This is called Economic Assessment of Geological Risks in Deep Geothermal Projects. And I would like to start with the motivation. So what is the starting point? Why are we doing it? So there are two German industry associations, DGMK and I have to remove that one, and BVEG, who have jointly published a new guideline providing a standardized method for the geological and economic assessment of deep geothermal projects. I have to say, you can find it in the internet. BVEG has it on their homepage, but the current version is still only in German. We are updating this version as we speak, and then the final version will also be published in English, but that will take a few weeks. Nevertheless, today I will give you the overview, what is in there in English already. So the motivation is what you see on the lower right of this slide. We want to support a strong ramp up of deep geothermal energy utilization in Germany. That is obviously our origin, but also it is all applicable in other countries and other areas, because the purposes are very clearly applicable to all kinds of areas. Effective allocation of investments and subsidies, increased commercial success rate, increased insurability and applicability of financial tools, and an effective and safe project planning. So all of that obviously is applicable in a wide range. So move to the next slide. So this is important for me. So there's a long list of authors and co-authors. It's not just me, but we are 12 people together. And without going through all the individual names, it is important that the authors represent a wide spectrum of relevant geothermal players. So we are private and municipal geothermal entities. We are geothermal developers, institutes and associations, insurers, service companies, and even oil and gas companies are involved, have been involved here. And that's why we believe we can address this guideline and the contents of that to all entities and individuals who are involved in planning and realization of deep geothermal projects. Excuse me. So the challenges are primarily the typical challenges of geothermal projects nowadays. And it's the key hurdles, which are front-end hurdles, the high upfront costs and the geological risks associated with it. So that is kind of exactly what we want to focus on: handling of the geological risks and uncertainties, and the translation of this into economic valuation. And at the same time, we want to give a structured approach, which is applicable to all relevant phases of the project, both in planning and realization. So, as I said, the key hurdle, high upfront costs and geological risks. We are applying a key concept, a three-step approach for the pre-drill assessment of geothermal projects. And obviously, it goes without saying, I'm talking about pre-drill assessment. This is the project assessment before it has been realized. And our three-step approach sees first the quantification of the geological probability of success. Second, how to deal with the uncertainties, the variability of the possible geological outcomes. And third, we combine both in an probabilistic economic project assessment. So what are we looking at? What are our applications? In general, this is applicable to all deep geothermal projects, we would say below 400 meters, kind of where real geology starts. It is written in a way, it is written for open hydrothermal systems. This is what we use as an example. But it can easily be changed and or adapted and applied to closed geothermal systems, to petrothermal systems, EGS kind of. And of course, it doesn't matter what we do with the heat at the surface, whether it is district heating or power generation. And the open hydrothermal system is shown on the picture on the left, the classic doublet with one well bringing up the hot water from the deep reservoir. The hot water is used at the surface for power generation or for district heating, or both, and the cool water is re-injected into the reservoir. This is not the key objective of the guideline, but we thought and we came across that this is kind of important to have a geothermal stage gate process proposed in the same context. And we all know that different companies, different projects require different stage gate processes. The one we propose is the 3-phase process where we start with phase 1 with the screening, project identification. We have a first gate, which is a preliminary project select. Phase 2, kind of the most important one in terms of geological risking, because this is where data acquisition, geological mapping, subsurface analysis, reservoir modeling, all of that happens, and that includes geological risking. This is phase 2. This is feasibility study and concept development, where we have the gate 2 as a concept select gate. Phase 3 would be detailed planning. This is technical well planning, economic evaluation, all the details before we get to gate 3, which is a FID, the final investment decision. And we recommend peer reviews at every gate. Peer review means inviting independent peers, experienced geologists, geophysicists, drillers, engineers, to look at it and to check it with a neutral view. But as I said, we combined feasibility and concept select into one gate. Others might have 2 phases there, but it really doesn't matter. And this is a key message for the entire guideline and for whatever I'm going to tell you in the next 15 minutes. This is a proposal. It's a logical and pragmatic approach, but it might need to be adapted to whatever needs are there individually, company-wise, area-wise, basin-wise, geology-wise, whatever. But the key principles we believe hold. And the key thing here we apply up front is a differentiation between geological risk and geological uncertainty. So we have on the left-hand side the geological risk, and this is a black or white, a yes or no. Can warm water be produced and re-injected? Yes or no? This is the geological chance of success. And on the right-hand side, we have the geological uncertainty. If we answer the yes or no question with a yes, the question now is, how much is it? And we know that geological parameter might have a large natural variability. So it can be little and it can be a lot. One of our co-authors, he had the example of the fisherman. You know, the angler goes to the river and tries to catch a fish. On the left-hand side, the question is, does the angler catch a fish? Question mark. If it's a yes, the next question is, how long is a fish? How large is a fish, right? So this is obviously, for me, it's a good analogy. And I'm starting with the left-hand side, with the geological risk. And this is, again, a proposal how to deal with the risk assessment, or better said, with the quantification of the geological probability of success, which we call POS-G. Of course, this is taken from the oil and gas exploration, but it's applicable here as well. And the POS-G is a product of individual factors, individual prerequisites, which are obviously a must to have heat production to surface. And we say the three prerequisites are reservoir existence. This is the first factor. That means the stratigraphic unit has to be present in the wellbore. If not, we don't have a successful well. Second is reservoir quality. This stratigraphic unit has to have porosity, permeability, open fractures. Otherwise, we can't produce hot water. And the third is hydraulic communication. So the wells have to be in hydraulic communication, but please not too close, because obviously we don't want to have shortcuts and produce the cold water immediately back again. So that is the three factors we are proposing. And the way these factors can be quantified, this is shown on the right-hand side. So we advise to use the chance adequacy matrix from Pete Rose. This works like that. So on the x-axis, you have good news versus bad news. So good news to the right, bad news to the left. And on the y-axis, you have data quality and data quantity. The more you know, the higher you get on the matrix, and the more specifically you can define whether you have a high probability or a low probability of success. So we have plotted in some arbitrary numbers for every factor, 1, 0.9, and 0.8. Multiplying those would result in a POS-G of 72%. But as I said, this is arbitrary. And the quantification of these risk factors goes via geological analysis, the quantity and the quality of the database. Of course, the maturity of the geothermal system. When you drill into a system which has been drilled 10, 20 times in your neighborhood, this gives you obviously much more confidence and higher probabilities. Regional analogs. And as I said in the beginning, this is a proposal to use these three. In other areas or in specific areas, you might want to use other factors and define that yourself. For illustration how this can work, we have selected two examples. And I would like to start on the right-hand side. So this is a well-established geothermal system. Let's say Paris Basin or the Bavarian Molas around Munich, where there are so many geothermal plants in existence already, where the database is nearly complete, and where analogs are all over the place. And here you can say that the risks are very low and the probabilities are very high. So in that example, we have put reservoir existence and hydraulics to 1, means 100%, and the reservoir quality has the only very small risk to 0.9, which gives us in combination a total POS-G of 90% in a well-established, proven geothermal system. In comparison to that, we look to the left where we have a more explorational setting. Again, these figures are all arbitrary, but it's an explorational setting. It's a first test of a new geothermal play in a basin where there's nothing yet. So the database is incomplete, and with incomplete database, it's difficult to give it more than a 50-50 on these factors here. We assumed that the stratigraphic unit, a carbonate or a regional sandstone, is most probably there due to geological reasons, so that is a higher probability. But when we multiply these 0.5 times 0.5 times 0.9, we have quite a low probability of success in the first place. But the good thing about geology always is we can de-risk it by additional data, 3D seismic, different ways of data collection. We can most probably move the location of these dots here from here to there. But if the data shows there is nothing, it might move into the opposite direction and gives us a very low chance of success afterwards. But it's useful to know that pre-drilling decision. So that's the overall concept for the POS-G calculation. And to do that, obviously, there's a lot of geological knowledge required. So we have, for the subsurface mapping, we need seismic interpretation. Perhaps we even need seismic acquisition first. Processing, interpretation, time depth conversion, amplitude analysis, structural mapping, and so on. A lot of very specific work packages here during the subsurface analysis. And it continues with the reservoir evaluation. There we have the logs from regional data, log interpretation and correlation, sequence stratigraphy, perhaps, facies interpretation, mapping, parameter mapping, etc., etc. A lot of, again, specialist work to be done here. And last but not least, the well planning, pressure analysis, trouble zones, completions, stimulations, casing setting depths, mud system selection. All of that needs to go in here. And again, peer reviews to kind of get a neutral view on all of that work. So that is a prerequisite for POS-G calculation and for a sensible quantification of these risks, but also for the right-hand side of my opening slide, for the evaluation of the uncertainties and the geological variabilities. And that's what we are looking at on the next slide. So while we discussed the geological success first, we're now here where we look at the uncertainties, the geological variations. Is it little or is it a lot we can gain here? And the key parameters for geothermal projects, temperature and production rate, they are again a product, at least a production rate, a product of various other factors like thickness of the reservoir, like permeabilities, KH, things like that. And all these parameters can be represented by parameter distributions. And these parameter distributions can be multiplied in a Monte Carlo calculation and will then result in a cumulative probability distribution of the geothermal power. So this is again an arbitrary plot. Probability on the y-axis, cumulative probability on the y-axis, geothermal power on the x-axis. And there are tools offering it. Obviously, there are software packages like GeoX, which is used in oil and gas, at risk, a plugin into Excel. But what we propose is to use Doublet Calc. This is an open source tool available on the homepage of the TNO. This is an Institute of Applied Science in the Netherlands. Quite easy to apply, specialized on geothermal applications. So it is made for exactly that. So have a look. This is an easy tool and you can easily play around with it. But the important thing is we cannot predict the geological parameters in 3-4 kilometer depth. We can only predict the range of possible outcomes. And that's why we apply here probability distributions for geological parameter prediction. And the next step is, because we can't use the full distribution curve for our project planning or for economics. Obviously, theoretically you can, but practically you can't. So, so we have to represent this distribution curve by deterministic cases. And there is a guy called Swanson who kind of invented the Swanson's rule, and he has invented the 30-40-30 rule, and that gives us the P10, the P90, and the P50 case of this distribution curve, assigned with the probabilities: 30% probability for P10, 40 for P50, 30 for P90. And that is a best statistic representation of the full distribution curve. So we can replace this continuum here between little and a lot we can't work with by these three defined scenarios. And this is an important step, to have these scenarios and have the assigned probabilities. And that is clearly much better than a best guess assessment based on arbitrary assumptions. And these three scenarios are important both for the technical detailed planning, because obviously you want to have your facilities and your well design adapted to your scenarios. And we use them also for economic calculation. And that is the combination of both, the combination of the risk and the uncertainty, which is then combined in a probabilistic economic valuation. And how are we doing that? So we calculate the net present value for all of the scenarios. So we call it NPV. So all the economic parameters, cost, revenue, OPEX, staff, all of that goes into this scenario calculation. P50 scenario, P90 scenario, but also the failure scenario. Unfortunately, this is a negative scenario, which is part of the equation. And then we risk weight all these values through the tree into an EMV, and EMV stands for expected monetary value. This is a risk weighted value of the entire tree. And all values of the system, of the project, all upsides, all risk and uncertainties are integrated into that one economic indicator. And the good thing is this indicator gives us then a project benchmark. We can compare different projects based on this. We can do our portfolio management based on this, and we can base our investment decisions on it. Because from a portfolio management point of view, investing into negative EMV projects might be successful because you still have positive scenarios up here. But if you do that always, you will most certainly lose money. So an additional information we can get from that EMV tree is where is value created in a project like that. Of course, value is created by the geothermal power we are generating here in these scenarios. This is a prime value creator for a geothermal project. But when we look at it, de-risking, mainly de-risking here, but also de-risking here and moving it into the higher scenario direction, this also creates value. And reducing risks creates value. And there are means to do that. How can we reduce these risks? What is the risk mitigation possible here? I'm sorry, that was the wrong one. This is the one. And we can risk mitigate through additional data. I touched on it already. So further data acquisition can significantly increase or also significantly lower the probability of success. And in both cases, this supports the right economic decisions. Government programs, as we see that in Germany, in some areas, in some federal states, for geological data collection, seismic, exploratory drilling, also serve to reduce the exploration risk because they give us additional regional data. And within our co-author team, most important, 3D seismic data is nearly always essential for minimizing risk and for a precise targeting of the well and for effective drilling. So we were thinking of, is that a general recommendation? Always do 3D? I would nearly say that. There might be the one or the other example where you can skip that, but in 95% of the cases, we would strongly recommend to have 3D seismic available before planning the first well. So that is the de-risking through additional data. On the right-hand side, we have de-risking through skills and experience. So application of experience, subsurface data interpretation helps a lot. Application of optimized well planning and drilling operations as well. Application of optimized reservoir stimulation and well completion, of course. And not to forget the application of established HSE concepts for safe project execution, also always important, because as soon as you're not applying that, it might get quite expensive. And I mentioned it twice already, application of peer review schemes, also important. So that gets me to my last or second last slide, which is a bit of a summary and the takeaway. The ramp up of geothermal energy, which we believe is very, very necessary for the energy transition, cannot be achieved without the intensive application of standardized risk and uncertainty assessment. That was our motivation, and it's still our belief. And it's important for 4 main areas. First, funding and insurance and state subsidies. So the selection of the right projects, the allocation of funds and subsidies, and last but not least, the insurability of a project. We need to know the risks, otherwise no insurer would insure it, dry hole against a dry hole, for example. Second is the cost reduction. All what we've been talking about here is important for cost reduction. We need to know where the main risks are. Only then can we mitigate them. And we need an adequate design for wells and facilities. So as soon as we overestimate the results, we might over-design the facilities, and that costs money. Same in the other direction. De-risking, acquisition of the right data, of 3D seismic, geological assessment based on skills and experience, and portfolio management. And this is something I haven't really mentioned yet. But since we are dealing with projects where there is a remaining risk always, and we can't really avoid it, we have to start thinking about risk sharing and partnerships and JVs and risk diversification across multiple projects. Nobody would want to put all the eggs in one basket here, because if I spend all my money in one project, this is not really wise. I would better share it, divide it, diversify it, and put the money into multiple projects with reduced shares. This is what portfolio management is about. And the analysis given here, the process, the risk and uncertainty analysis proposed here would give you all the tools to do a proper portfolio management. Now comes the last slide. Thank you very much for your attention. And I'm happy to have questions and a good discussion, and we still got time to do so.
Thank you very much, Gregor, for a very concise and value-driven presentation. Actually, a super important matter in terms of looking at what the future geothermal projects are going to look like. We did have quite some dynamics in the chat box when it comes to questions. So we'll jump straight into it. We had the first question from Lena Broadley, and she says, Gregor, how does exploration fit into the stage gate process? Just thinking about areas where there's very little data to identify the potential.
Yeah, so that would be for me the phase 1. Of course, you would first try to understand the place you've got in your basin and the geological risks. Whether you want to start with phase 2 already depends on the outcomes of your first gate, and then you would start with data acquisition. So phase 2 is kind of the most important one. You shoot perhaps 2D or other geophysical remote sensing stuff. Perhaps you have wells, perhaps you have analogs. So phase 2 is clearly the most important one for an exploration approach. And then you might come to the decision whether to go for a well and risk it or to acquire additional data.
Thank you. We have a question from Christian there. He says, could you explain in more detail the difference between the reservoir quality, which would include permeability, that is conductivity, and the hydraulic communication?
Yeah. So, hi, Christian. Good to see you. There is
likewise.
The hydraulic communication depends so how to say that? So in a one example, you're looking into a clastic reservoir, and you have faults between your the two legs of your doublet. Imagine this fault is sealing, then you deplete the one leg where you produce, and you pump up the compartment on the other side of the sealing fault on the other side. So that's where you don't have communication, and you can't do that for long because you get too high pressures on your injection well. This is obviously the example where you don't have communication. The other example is when you have a fractured reservoir and you're drilling too close to each other, and you get a conduit from one well to the other, and you have the shortcut, and you produce the cold water back again. That is the classic hydrothermal risk. So it depends a bit what kind of reservoir are you talking about.
Right. There was a comment on that from Adrian that said that he thinks that the hydraulic communication could be viewed as reservoir connectivity, both in a vertical and horizontal sense. So thank you for that comment, Adrian. And then Stewart asked exactly why 3D seismic. I'm looking at closed loop rather than EGS, hence the question.
So the way I understand closed loop, obviously, you are more independent of your reservoir, of course, and you are more independent of your of faulting. But when I see typical projects for closed loop, you know, in northern Germany or Denmark, where you would try to get into salt or so, you drill deep wells and you have risky well paths along a salt structure, for example, or through fractured or faulted overburdens. Even there, for the well planning, it might be very useful to have the 3D seismic. But I agree, for hydrothermal, it's essential. For closed loop, there might be examples where you can live without.
All right, thank you for that. Lena sent in a question after that, and basically, well, a comment in a question, completely agreeing on the value of 3D data, but she's really interested if you could share your experience on the challenges of acquiring good quality 3D seismic in urban areas, which is usually, where the market is, for example, for heating. So public support, logistical challenges, and the impact of urban noise in particular. Are there good ways to overcome these challenges? That's a great question.
Yeah, no, that's a good question, and we have examples in quite a number of cities. Obviously, I'm coming from the German perspective, and I'm sure we've got that in French cities as well. And in Vienna, they shot 3D seismic. They shot 3D seismic in Munich. They're currently shooting 3D seismic in Münster, a city in North Rhine-Westphalia. So they have developed special applications for that already. So DMT is kind of specializing on it already. They are obviously shooting the 3D seismic in Münster nowadays. It is possible and it's viable. Obviously, there is always the permitting is always an issue, but it is possible, and the quality of the data is good enough. And there are good examples, really good examples for it.
Yeah, I think there was an additional comment that came in from Daniel Bendiez, and he said he's working in geothermal with 3D seismic in Munich. That was shot in a very densely populated area.
Yes.
So the data quality was excellent. Basically, a positive response, kind of emphasizing what you just mentioned. So that's nice to see. We do have an additional question from Adrian. He said, kind of going back to the connectivity topic, in the geothermal context, is equivalent to water flood where in this case you want a pressure maintenance rather than flooding, compared to the heat maintenance rather than short-circuiting cool water. What's your thoughts on that?
Um, I'm sorry, I read through the question again because I didn't get it by ear.
And Adrian, feel free to clarify if you want to
Yeah,
clarify the question.
perhaps that would help, Adrian.
Yes.
Are you on mute, Adrian?
Okay, is that any better?
Yes.
Can you hear me? So, yeah, I mean, what I was trying to get across is just this, um, the two, or the many sort of functions of recirculating or pumping water in oil and gas. In oil fields, obviously, you want to flood a oil saturated formation, but also you want to keep its pressure up for other productivity reasons. So, like that. Now, in geothermal, you want to be careful about keeping the sort of circulation of cooler water away from your hot resource, but you also want to keep the heat up as well. So the heat is the resource akin to the hydrocarbon. So it's just really what this whole presentation, which has been really interesting, has highlighted to me is these such direct equivalences of oil and gas development, appraisal, exploration into the geothermal world. And I think that is something that I'm taking away from this as a sort of a big reinforcement. I've always had that view, but I suspect other people, yourself included, have also had that long-standing thought, and it's how can we promote that into the geothermal world more widely. So,
Yeah.
thank you.
Thanks for the feedback. And an answer to your point was heat maintenance rather than short circuit. The problem with geothermal power is that it is dependent, though it's a product of heat, of temperature and rate. So if you reduce the rate to keep the temperature, obviously you don't produce enough power, geothermal power any longer. So therefore, this has to be mitigated during planning and can't be mitigated during operations anymore.
Right. Thank you, Gregor. Thanks, Adrian. I did miss a couple of questions in the chat, so we'll get to them. One that came in from Jamie Venel says, how would you deal with risking enhanced geothermal systems where the permeability and hydraulic communication is created as part of the drilling process? Would you only consider reservoir presence, for example?
Yeah, so this is most for EGS, you have to obviously adapt what we have presented here a lot. So EGS is most probably furthest away from what we have taken as an example here. So, but also in EGS, you can risk factors are frackability. What kind of rock do I get there? Is it granitic? Is it metamorphic? Or is it all sedimentary rocks? So can I really frack them? How thick are the carbonates I'm going to frack? There is obviously risk factors, but these risk factors have to be designed differently. And the same, when we are talking about permeability and natural production rates, this has to be transferred for frac size. And so it's a different modeling behind it. But the general concept of risk and uncertainty can still be applied, but I see that the application is quite different.
Absolutely. And just to add a little bit to your comment there in terms of the EGS, because that is something we're working with right now in the United States,
Yes.
looking at 300C. Essentially, it's how do you define what the engineered rock volume is and which part of these fractures are actually connected and how long can they maintain the flow. So I think it gets a lot more complex in a different way. So that could be a totally different talk we can have. Um, Another question from Marius that came in, he said, by what magnitude is a risk analysis necessary for a geothermal project in comparison to oil and gas, considering the longer ROI and the other aspects?
So it's even more urgent, I would say, because obviously we have to be more risk averse here because the economics aren't comparable or much lower than producing oil and gas. So therefore, from my perspective and from the perspective of my co-authors, it is even more required in geothermal.
All right. Then the following question from Edna says, Gregor, thank you for your insightful presentation. Could you please elaborate on the weaknesses of the proposal for the quantification of POSG presented on your slide 8?
Yeah, that is a good question. And but I see on screen Uli Möller, who is the expert on that, who did that for Wintershall for many, many years as a key peer reviewer. And I would give that question to Uli.
Thank you, Gregor. Hi to everybody. Yeah, I was just wait a minute. Thinking.
It was about the weakness.
On the weaknesses. Okay, the weaknesses of this plot. I mean, the weakness comes with that normally everybody has a different understanding of and a different naming of what is 70%, what is 80% POS, and what is likely, what is very likely, and so on. It's very clear on the far ends, but if you're somewhere in the middle, then it gets difficult, and everybody else has a different thing. So that is one of the weaknesses, and how you can overcome that is basically that you have very clear definitions of what you are risking. And that possibly comes back to what was discussed before. So the difference between reservoir quality and the connectivity. So that needs to be very clearly defined. What are we risking where? And if we have any results in there, then you have to look at the database, the quality, data quality and data quantity, and to bring that into the game and to come up with a clear value there. There are several methods how to do that. You could do that via peer reviews. You could do a call within the company. Everybody could shout out a value, and you take the average of that. Or so there are several methods which you can read off, but that's basically it. So you need clear definitions of how to do that.
Yeah, and if I may add to that, Edna, if you deal with 1 or 2 or 3 projects, this is really difficult and weak. So you really need to have experts with a wider view who have seen larger numbers of projects in the past, who have got a larger reference base they can draw on. And that is why I mentioned so often peer reviews, to have other people looking at it who have seen different projects and have that experience from a larger background. And that's why I took Uli, because he did it for many years for global Wintershall, giving him this large background. And this is something which is really recommended for geothermal projects as well. Get experts, get external people who can look at it.
Yeah. So experience density, essentially different perspectives from projects that people are working on. I don't know if you're all aware, but there is a consortium right now ongoing called the GEOT consortium between Project Innospace and SPE, and essentially is a conglomeration of experts, whether technical or not, from different domains in the oil and gas, and also geothermal, having that difference in experience and trying to pitch in with that. I think that sounds a bit analogous to what you said, Gregor. We do have a question from Scott Hess in here that said, do you include technology risk for technologies that do not have historical and analog data that can help steer your risk and uncertainty quantification?
Yes, very good question, and very good that you're mentioning it. We have DGMK and VEG are currently working on a second guideline. So the first guideline was dealing with the subsurface risks. The second guideline is dealing with the operational and the drilling risks. Not yet published, but it will come early next year as well. And it has to be taken into account mainly when you drill into new areas where you have to kind of take analogs from somewhere else and bring it into your project. And also when you apply new technologies.
All right. Thanks, Gregor. There's one more question from Putri Wahid. I hope I said that correctly. It says, thank you for the very insightful presentation. How much knowledge and experience can we bring and adapt from geothermal system in countries like Indonesia, Turkey, Philippines, where they may have low enthalpy but have higher chance of seismic and volcanic activity into Europe? Is there already adaptation that you may know of?
To be honest, I don't know of anything because obviously my focus is Central Europe so far, and all of my core authors mainly worked in Europe. Some of them have Iceland experience, but since that was not the key focus, to be honest, I can't answer that question. But I can only invite you to look at the guideline and to look at the principle and see how that is applicable to high enthalpy areas as well. So, but I can't answer that.
All right. Thank you for that. I think we've covered all the questions. There's been a couple of comments in the chat box that I'm sure the audience can take a look at. Obviously, from these questions and discussions, a lot of other events could come out of this. But at this time, I think we've covered it all. Unless Gregory, do you have any additional comment for the audience before we call it a day here?
Yeah, so this last point, Scott came up with the operational risks, and that is something we are working on. This is something which will be available, and hopefully we will publish that in English straight away. You know, but you will find it, even if it's in German, you kind of pull it through DeepL or so, then you've got the English translation. But we are working on that as well. So we are really happy to distribute it, and if somebody needs the link, perhaps we can provide it through Gabrielle to the group.
Yeah, absolutely. If you share that with me, we're going to share the recording, and if you're okay with it, a sanitized version of the slides. And then if you have anything else to share with the participants, we can do that. There's actually a couple more questions came in. Do you have a little more time, Gregor?
Yes, I've got time.
Awesome. So Ray Alvarado asks, can you expand a bit regarding the risk sharing that you mentioned earlier?
The risk sharing, yeah, that means if I have a limit, yeah, so risk sharing means for me that a well or a doublet or a project which has a certain risk, I don't want to put all my money into it, but I spare funds for different projects. And in every single project, I share the risk with others in consortia or joint ventures or with other partners. And so if one well goes wrong or one project is not successful, I can hopefully still live with the other successful projects and compensate for it. So this is like an exploration portfolio in oil and gas. Don't put 100% on one project, but share it with others and distribute your funds across a number of projects. That is the recommendation. Of course, as a local player, as a local player, as a local utility drilling one doublet, this is easier said than done. But clearly there, it is very important to find risk mitigation measures and get other partners in to share the risk. That is what we mean by risk sharing.
Gotcha. Thank you. Adrian says, earlier when we talked about the guidelines, have they been shared with financial institutions to get a sense of how they would view this approach?
Yes, so as I said, we have insurers. We have two insurers as co-authors. So the insurance companies were involved in writing it. And we learn already, though it's not yet the final version, that investors and other insurers want to use it as an evaluation tool for their risk quantification.
All right. And then Stan Lu comes in with the last question for the day. What is the most important task of peer review? What's in your view the most important?
So perhaps that comes right after drilling and producing.
All right. All right. I don't think we have any. Oh, wait. We have comment. Yeah. Thank you, Lena, for being here. I don't think we have any more comments and questions. I'd like to thank you, Gregor. And thank the audience for being here today. We are going to continue with these talks in the near future. We're trying to basically echo the geothermal message across Europe and beyond. And I think it's part of what you were talking about earlier, Gregor, is more experiences, more perspectives. So thank you for taking the time today. Thank you, SPE Germany and the team for making this happen. I will follow up with the slides and the recording to all the participants, and have a great evening.
Thank you very much. All the best.